It's Finton Quill. So what I'm going to talk about today is just big data and IoT. So obviously, when you're at conversations, having conversations here and at conferences here, you see a lot of different choices. So I just thought I'd put this funny picture up just for the sake of it. So there's many choices out there, but then like what do we want to do to make these choices? What are the things we need to consider? And I think when we step back and a lot from a business perspective, I think there's three main things. From your total cost of ownership, you need to think of number one, your hardware. Number two, your software, and number three, your developers. And more nowadays, the developer cost is completely ballooning compared to the other two costs. So what can we do to actually make that a bit more efficient and to drive our costs down? So as I say, from a hardware perspective, there's lots of things we need to learn. I feel like many engineers nowadays, many software engineers are actually like leaving hardware behind, and they're not seeing some of the advances that are happening, and they're not writing their software accordingly to work on that hardware, which is something that I feel that we've done at our company. But just in terms of like what do we need to think about with hardware? So number one is memory. Memory is exploding in terms of size, and the cost is going down. And now 1 terabyte of RAM in a machine is just commodity. That's pretty much standard. And there's bigger machines coming along. So I played with a 32 terabyte RAM machine a couple of weeks ago. Obviously, you know, that comes with a cost, but you know, the cost of RAM is coming down, and more data can fit in RAM. We can also do in-memory compression is coming down the line as well as coming directly in the operating system, so you can take advantage of compression in memory. And then there's also the idea of transactional memory, which is very much upon us now as well. Another consideration with hardware then is storage. So there's huge advances in storage in the last couple of years. So now we've got non-volatile DIMMs, we've got NVMe flash storage, which are like orders of magnitude faster than the traditional, standard spinning disk media that we're used to dealing with. And then there's this whole hyper-converged approach as well, and the idea of, once again, compressing data on disk. And then the third point would be parallelism. Obviously, we've got parallelism inherent in machines now that are multi-core machines, so you want to be able to take advantage and write code to properly take care of the multi-core machines. And then even in the instruction set level now, we also have vector instruction sets directly in the machine instruction sets. So we want to take advantage of those, and we want to write our software appropriately. And then we also want to run effectively in a distributed manner as well, so to be able to fan out over multiple machines, but do that efficiently, which is the key here, doing it efficiently, because a lot of the tools that are out there nowadays are extremely inefficient for dealing with clusters of data. And then there's the idea of file systems as well now. Obviously, there's many file systems like BGFS, BTRFS, etc., that can take advantage of this distributed parallel file system nature and give us one view of the data. So that kind of covers a lot of the hardware side of things. And as I say, today I'm here to talk about like big data and the IoT side of things from a time series aspect. And one big thing about IoT is everybody's talking about big data, oh, unstructured this, unstructured is becoming bigger and bigger and bigger. But then at the same time, they're telling us that IoT is becoming bigger and bigger and bigger. And that's something that I still find trouble kind of like equating those two things, because the most sensible thing is anything I've ever seen from an IoT device is inherently structured. So if anything, the size of the structured data is going to completely swamp the size of the unstructured data going forward. And as well as that, IoT is inherently time series. Everything is timestamp, ID, value, whether it's temperature, whether it's pressure, any sort of measurement. So it's all time series nature. So it's structured and or semi-structured data. And then it's also about doing analytics at the edge, so not just having it in a massive central data server, but actually being able to do some of the analytics, say, directly on your Fitbit, et cetera, et cetera. So for that, then, you need a small footprint. So you need to be able to run in these small devices, and typically run on some sort of like ARM-based architecture, or like devices like the Intel Quark that's coming out. And then you also need to be able to deal with streams, and you need to be able to deal with data as it's coming in, and not just when it's stored, and tabulated. And then you also need to be able to deal with micro-batch data, especially if you're in areas where maybe there's poor connection and you're sending data back over the wire, so maybe it has to buffer it and then push it up in batches. So these are some of the considerations that we need to think of when we're thinking of IoT and big data going forward. So about our company, KX, we've been around since 1993. We're part of First Derivatives Group, which is a publicly traded company. We have a relatively large user community, not as much as other technologies, and these are some of the industries that we're involved in. So we've mainly been involved in the financial services industry, so we've been dealing with banks for about 1993 onwards, so quite a bit of time. And finance in my opinion, has been ahead of a lot of other industries in dealing with big data, and especially dealing with streaming big data as well, because it's been capturing data from the market since, you know, the 70s and even further before that. So you got the idea of like the Lambda architecture and the Kappa architecture. That's not big news in finance. You know, these high-frequency traders and big investment banks have been doing this for a long time. So what can we learn about this, and what, you know, we're seeing these volumes now coming out into other industries, so what tools are available to deal with this? And as you see here, there's just some examples of graphs where you got like 18 billion quotes in a given day for just one exchange, and there's multiple exchanges out there. So this is multiple terabytes for just one single data feed. So how do we capture that and store that? So that's what I'm going to try and talk about a little bit more. So our product, what we do is we do streaming, real-time, and historical data. So it's not like a lot of other solutions out there where they just do the streaming part, or they just do the in-memory part, or they just do the on-disk part. We do all three of these facets, which I think separates us from a lot of other technologies out there. And this is just another, you know, funny diagram that I have here about small data, big data, et cetera, et cetera. So our main product is called KDB+, and it's an integrated database and programming system. So there's two versions available. There's a 32-bit free version that you can just download from our website, kx.com, and play around with. And then we've got a 64-bit license version. And there's no difference between the two versions other than the address space limitation. So you just got a 4 GB address space limitation with the free version. And then you're limited to basically your RAM on the 64-bit version. In terms of some of the features, we run on standard operating systems and hardware. So we've got builds available for OS X, for Windows, for Spark, Spark chips for Solaris, and also the Intel on Spark, Intel on Solaris, sorry, and then also Linux. So about, I'd say 90–95% of our customers are using standard like Red Hat Enterprise Linux. Yeah, and then we're hardware agnostic as well. It's a purely software solution, so it's about 400 kilobytes in size, so it's pretty small. So it fits typically inside the cache. We support compression as well, so we can support compression on disk, in flight, and then when you're sending data over WebSockets as well. So we can take advantage of all of the parallelism available on multiple machines, so multi-core machines, and in many machines in a cluster. And I missed the in-database analytics as well, so obviously a lot of people know about that nowadays. So separating it, traditionally, obviously people separated the analytics from the database. So now we're actually bringing that together, and that's you know, not new. And we can also support columnar, relational, and key value as well. In terms of the APIs, we support APIs for most major programming languages, so C, C++, C#, and these are all open source APIs. You can download them from our website and connect. And then in terms of some of the interfaces as well, we've got ODBC version 3 compliance, so you can hook it up to a Tableau server. And then we've got JDBC, HTTP, and WebSocket. The HTTP and WebSocket server are actually built into the executable. So then on top of the database, we've got our programming language queue, which I'm going to try and get into and show you a few examples. So what are the facets of the queue programming language? Well, it has SQL-like semantics, so it has CRUD semantics, so select, update, delete, et cetera, et cetera. And then it also supports array or vector operations, and so that's very powerful then from a programming efficiency perspective, because you basically get rid of a lot of the traditional control structures that you have in other languages like if loops, do loops, while loops, because our operations run over the entire vector. So it's very easy, and so it really does reduce your code base. And we also have native time series support, which I'll get on to next. And then it also has functional language features, and that's built directly into the language as well. So you've got the functional and the query in one, so it's not like SQL and PL SQL where you kind of have this two kind of separate things. You can actually merge them both together with us and also create your own user-defined functions directly into the queries. So in terms of some of the time series analysis, what are the things that we support? So we've got native temporal data types. So we've got dictionaries, tables, keyed tables, nanosecond timestamping, millisecond timestamping are all first-class citizens into the database. They're not some like afterthought or some library that we load in after the fact. So as I said, we do high precision nanosecond timestamping, which is exceptionally important in a lot of the IoT industries nowadays, where they're doing sensor analytics and reading off devices. And then we can do temporal arithmetic, so adding, dividing, you know, subtracting dates, which is surprisingly uncommon in many database platforms. We also have the ability to do bitemporal joins, which is not very common. So that's like if you've got two different time series data and you try and join them together, and even if they're mismatched on time, it will do a lookup back in time, rather than say if you did that with a traditional SQL join, you just would get a mismatch. We can also join the time series on the fly as well. So as the data is coming in off the wire, we can do a join even before the data is actually tabulated. So this is a sample architecture diagram here. So you got your data coming in on the left, and that could be from some like feed handler written in a compile language like C, C++. And that would be going into our events engine. So all of these blue boxes here are all just processes written in the Q language. So the data comes into the events engine first, and the events engine is typically called a ticker plant in the financial world. That's basically a data distribution engine. So the first thing it does is it logs the data down to the log file on disk, and that's for recovery purposes. So then if any of these in-memory systems go down, you can replay the data from that log file. So the simplest example of a subscriber to this events engine would be what we call the real-time database. So that basically just opens a fire hose and gets all of the data. So it gets larger and larger throughout the day. So it's quite memory intensive, but it's not particularly CPU intensive because it's just doing simple append, 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 append. But then you can have specific streaming query engines or CEP engines. And what they can do is they can maybe subscribe for a subset of the data. Say, I want to subscribe for these 4 stocks that I'm trading, and I want to calculate the volume-weighted average price or something like that as the data is coming in. So that's going to be a little more CPU intensive because it's doing calculations on each message as it comes in. But then it's going to be a lot less memory intensive because maybe then you only have maybe 1 entry per subscription in your table, so it's a lot less data. So then if you want to get that volume-weighted average price, you just hit that engine and you get basically instantaneous results. And then what happens at typically end of day or any pre-configured interval is that data in the in-memory database gets dumped down to a shard on disk. So it creates a new day on disk. So everything but, say, today's data is residing on disk. But the querying is exactly the same, whether it's the streaming query engine, the real-time database, or the historical database. It doesn't look any different. So I'll just run quickly onto a demo. So I'm running this on a server which is based in New York. It has about ½ terabyte of RAM, and it's got 22 terabytes of real New York Stock Exchange data for about 3 years. So if we just look at some of the sizes of the data set, so our quote data set is 538 billion records. Our trade data set is 253. So there's over 1.2 trillion records between all of the different tables. So basically, the Q language in action, it's an interpreter environment, so you can just start typing. So I can just create, say, a list of 3 numbers. Oh, it's not coming up here, sorry. I guess any questions? Or?
Everyone's 15 minutes for questions. There was a diagram where you showed about the structure.
Yeah.
You mentioned that the data comes in with the events engine. How does the data come in?
It typically comes in over IPC. There's a few different ways you can do it. So you typically open a simple TCP/IP socket connection, and you just push the data across over the wire. So as I said, our whole communications protocol is documented and it's available, and that's what all of those APIs that I mentioned do as well. Like they just open a simple socket connection, push the data across. Another thing they can do is you can actually load shared objects into the actual execution space. So you could actually push data in that way as well. So it's actually just running in the same namespace. And that's how, say, our Python API works, for example, is actually you can run, say, like pandas functions directly on the data in our database because it's running in the same memory space. So there's a few different ways you can do, or else you can load in from a flat file as well. It could just be loading from a CSV file or something like that. So you got a few different options there. But for that particular kind of diagram that I'm showing, it's typically they'll open a TCP/IP socket connection from the data source and push the data across. Yeah. But yeah, doing the shared object is typically faster because obviously it's working in the same memory space. So you don't have the TCP/IP overhead then. Yeah.
Yeah. What kind of analytics is possible with this language beyond SQL queries and like SQL-like?
Yeah, so it supports all of the standard SQL-like analytics. So it has, as I said, the CRUD semantics, and also has, as you saw, some of the moving averages, weighted average. So it has a lot of statistical functions, it has a lot of trigonometric functions, it has a lot of matrix functions built in. We're working on a lot of like machine learning libraries now. We don't really have that kind of available, but that's stuff that we're working on, and we're probably just plugging that in as modules. And then if you go, we actually have a GitHub repository as well where people have contributed a ton of like libraries that they've written on top of the base product itself, because the base product itself, we try and keep it as kind of tight as possible. So it has about, I think it's 225 functions in total altogether, so a mix of algebraic, trigonometric, you name it. Most of them are there, and some basic matrix functionality as well. Not like huge amount, but some basic ones. Any other questions?
Thank you.
Okay, cool. Thank you very much.